All right, so I know there was a lot of stuff this unit. See if we can narrow it down just a little bit. One of the things I see on your review sheet is a term called the plane of the ecliptic. And the planets, see if I can pull up a pencil here, the planets orbit the sun in pretty much the same plane. So this is called the plane of the ecliptic. So the planets all orbit the sun in what's called the plane ecliptic. One of the things I see on your test is the Earth's tilted axis of rotation, and actually you can see it here, and that is actually why we have seasons. You can see that actually the axis of rotation is tilted, and the specific degrees on the next slide is 23.5 degrees. It's tilted. And the other thing is it's always directed to appear is the star called Polaris. Okay, so it's tilted 23.5 degrees, always to the star Polaris as it orbits the sun. All right. The Earth's tilted axis of rotation and the Earth's seasons. So that must be on this slide. Okay, so as the Earth orbits the sun, its tilt actually is sometimes directed to when its north pole is directed towards the sun. Actually, then in the northern hemisphere, we experience summer. Specifically, on June 21st, thereabouts, I think must be on the next slide, we have our summer solstice. And when we're having summer in the southern hemisphere, they are having winter. So I think that's kind of cool. So then, if you take 12 months for the Earth to complete one orbit about the sun, of course, that divided by 4 is 3. So every 3 months, we are 1/4 way around the sun. So here is the Earth orbiting the sun. You can see the Earth's tilted axis of rotation. I mentioned when the Earth's north axis of rotation is pointed towards the sun, that is our summer solstice in the northern hemisphere. 6 months later, it's our winter solstice because we're directed away from the sun. And actually, this is a pretty good slide. Can you see where if you are here in the summer solstice, if you are near the North Pole, as the Earth spins on its axis, you're going to have all daytime, all daylight, all day long. And then over here, as the Earth spins, can you see that as the Earth spins, actually you're going to have night. You are not going to have any daylight, so nighttime. It's darkness all day long as the Earth spins. So we have 6 months apart, we have our summer solstice and our winter solstice. And then between there, of course, we have, as we're leaving summer, going into winter, we have autumn, and we have our autumnal equinox. So about September 22nd or 23rd, we just kind of passed not that long ago. Well, I guess it's been a few months now. Time flies. So we call it an equinox because 12 hours of daylight and 12 hours of nighttime is what everybody gets at all lines of latitude. So that's one equinox. 6 months later, we have our spring equinox. That's my favorite time of the year. And actually then we also have, it's called spring equinox or vernal equinox. That's the same thing. It's March 21st, 22nd. And you're looking at, again, 12 hours of daylight and nighttime at all lines of latitude. So the big question about that. Speaking of lines of latitude, there are some special lines of latitude. Well, lines of latitude, those are the ones like this, lines of latitude that are centered on the equator. I'm trying to read my notes, what I have, where they begin, lines of longitude. Okay, so this is latitude. Okay, longitude are these guys right here, longitude. So longitude go from pole to pole. Okay, and I have in my notes, where do the lines of longitude begin? The lines of longitude begin at what's called the prime meridian in Greenwich, England, and they end actually they meet up at the international date line. You can't see it very well. Let me make it bigger. This is the international date line, which is kind of, if you take where they begin halfway back there, that's the international date line. Let's see, what else do I have? Variation in number of daylight hours. I think I kind of covered that a minute ago. Helpful lines of latitude. Oh yeah. So now the lines of latitude then go this way. Lines of longitude go this way. Okay, so lines of latitude, the biggie or the beginning line of longitude is the equator. Then we have, and actually this is a player when we talk about meteorology too, we have important lines of longitude in both hemispheres. In the northern hemisphere, we have a Tropic of Cancer at 23.5 degrees. We have an Arctic Circle at 66.5 degrees. And then, of course, we have the North Pole at 90 degrees. And then in the southern hemisphere, we have the Tropic of Capricorn at 23.5 degrees. And then we have the Antarctic Circle at 66.5 degrees, and the South Pole at 90 degrees south. So know those. Now this one is a little, must be the next table. So this is actually a little table to show you when approximately we have our solstices. Okay, winter solstice, December, summer solstice, June, and I used to go 21st to the 23rd, and it'll catch everything. Our vernal equinox, our equinox is in March. That's our spring or vernal equinox. And then we have our fall or autumnal equinox in September. And then I have in my notes, so if you are, I think, how would I say this? North of the Arctic Circle. So when I said if you're near the pole, the winter solstice, you're going to have 0 daylight hours. In the winter solstice, and in the summer solstice, you're going to have 24 hours of daylight. And the equinoxes, of course, you're going to have equal. All right. Variation in number sun rise and sunset. Okay. Sun and star rise. So if I were to ask you where does the sun rise, you would say it rises in the east and it sets in the west. So actually stars do kind of a similar thing depending upon kind of where they are. Stars, though, that are near Polaris. So where is Polaris? All right. So I said the north axis of rotation is pointed to Polaris, and we spin on our axis of rotation. So for that reason, actually, if you were to look at the Polaris, which is the North Pole, I'll put NP for the North Pole, which is Polaris. It's like a bullseye. You actually see stars going, counterclockwise around Polaris throughout the course of the night, like that. So if you make that big enough, actually they are going to appear to rise in they are going to appear to rise in the east and set in the west. Oh, darn it. I did it clockwise. Are you serious? I'm so sorry. It's counterclockwise. NP. Sorry about that. Counterclockwise. And that didn't work very good. Okay, so counterclockwise. So they appear to rise in the east. That's better. And set in the west. So, all right, and that's because the Earth is spinning on its axis. Circumpolar stars. Hopefully that's in the next slide. Okay, so there's my bullseye. And actually, the North Star, or Polaris, is in the handle of the Little Dipper. Isn't that cool? And here's the Big Dipper. And these are what we call star trails. So these would be going counterclockwise. Make sure I get this right. Yeah, rise and east. These are going counterclockwise. The stars are going around Polaris. And I do have a term on your test called circumpolar stars. So circumpolar stars are stars that actually you can see the whole circle. Okay, like these guys over here, these are not circumpolar stars because they go below the horizon. If they don't go below the horizon, they are circumpolar stars. Also on the slide, yep, you can use the star Polaris to determine which latitude you're on. The angle that Polaris, this should be latitude. The angle that Polaris makes with the horizon. So if I was in front of you, I could say we're going to put our one hand out and we're going to point it at the horizon. We're going to take our other hand and we're going to point it at Polaris. And then the angle that your arms make then is this angle right here. Okay, that actually is your latitude. All right, so for us, Polaris is about 40 degrees above the horizon. So our latitude is about 40 degrees. We see different stars throughout the year, and I actually tried to kind of show you this in one evening. So basically, if this is the sun, and this is the Earth orbiting the sun, and it's all about counterclockwise. For instance, over here, I think this is supposed to be February. In February, we see these constellations during our nighttime as we rotate away from the sun. And then over here, 6 months later, in, so that was, what month was that? That must have been August. Sorry, that was August. And then 6 months later in February, our nighttime, actually, these are the stars that we're going to see. So you're going to have a question about that. All right, on to part 2. I have a question about the solar nebula. So in general, the solar nebula was actually this kind of cloud of gas and dust that formed our sun and our planets. I'm going to have a question about when did the sun turn on. So in this picture, actually, it's trying to show you the formation of our solar system. And here the sun is on. And one of the last things that the sun did was create the solar wind and actually kind of cleared the disk. We talked about the plane of the ecliptic. Can you kind of see the plane of the ecliptic? All the planets orbiting the sun counterclockwise like that. So anyway, so the sun turned on how long ago? About 4.5. B stands for billion years ago. Billion years ago. So that's wow, about 4.5 or 5 billion years ago. Apparent retrograde motion of the planets. And actually into astrology, remember astrology, even though it has the word OL, has the ends in OLG, it is not OLOGY, excuse me, ology. It is not science. But astrology actually kind of introduces this idea of when the planet is in retrograde motion, what you can expect for your horoscope. So astrology is about horoscopes. Now, we do have retrograde motion, and the reason we have, what it looks like and why it occurs. Okay, this is what it looks like. So this is Mars, the retrograde motion of the planets. Planets actually will wander against the background stars. These are background stars, and this orange thing, that is actually the planet Mars. And we can see in November, it's going, excuse me, let's see. Yeah, and I think I'm going to change that up. In June, it's here. Okay, in July, it's here. And actually, that is direct motion. Direct motion. So it's supposed to go that way. Now, beginning about July to September, this is retrograde motion. Retrograde. And I'll try to kind of explain why that happens. Retrograde, excuse me, motion of the planet against the background stars. And then this is direct motion again from September to November. So the direct motion is just simply because as Mars orbits the sun, it actually, let's see, it's an outer planet. It's going a little bit slower than we are, so it's going to kind of look different against the background. It'll from our perspective, it will line up against different background stars. Now, this right here, this retrograde motion, actually has to do with when we, I wonder if it's on the next slide, when we, what we say, overtake Mars in our orbit. No, I don't see it. Let's see. Do I say why it works and why it occurs? So basically, if this is the sun, this is Earth, and here is Mars. And so the thing about it, I think when I told you a minute ago that actually Earth is going faster than Mars. So here's the deal: as Earth kind of catches up to Mars in its orbit, as it kind of lines up and what we say overtakes it goes beyond it, goes faster, then actually that's when we get this retrograde motion. I tried to explain it, I think, in my PowerPoint slides. All right, so now I have Kepler's 3 laws of planetary motion. So Kepler, oh yeah, here it is, duh. So here's that retrograde motion, and the blue is the Earth, and the red is Mars. And so Mars goes a little bit more slowly. So here, position 1, 2, 3, 4, 5, 6, and 7. So the Earth is actually catching up with Mars. And here about position 3, 4, 5 actually is where we're going to see that backward motion. Okay, right here, 3, 4, 5. And yeah, all right. So Kepler's 3 laws of motion. Is that what I have? All right. So here they are. His first law is the shape of the orbit of the planet. So actually it's not a circle. This is an ellipse. Okay, that's the shape of as the planets, the Earth and all the planets orbit the sun. Here's the sun. It's not really offset that much, but it's an ellipse. And ellipses have cool features in their center called foci. So the sun is at one foci, and there's actually two foci, two belly buttons. So one of the things you can see about the ellipse and the sun being at one foci is that it's off center. So when any planet is close to the sun, we call that at perihelion, and it was far from the sun, we call that at aphelion. So that actually is a player in his second law. So Kepler's second law of how the planets, he observed how the planets orbit the sun, is he said as they are near the sun, they go faster. Okay, this is perihelion. As they're far from the sun, they go slower. So it goes, okay. So that's the crux of it. And actually, it talks about equal areas, and this is the equal area, and it has to do with the fact that it's going faster here and slower here. Okay. All right. Oh, then the third law actually has to do with something I talked about a minute ago with Mars. I know it's got this funky thing here, but I said that Mars, where'd it go? Okay, this is how long it takes to orbit the sun, sidereal period. So I said that Mars goes more slowly in its orbit than the Earth. So you might say, well, of course it takes 1.88 years instead of 1 year compared to Earth, because it's got a larger ellipse that it needs to orbit the sun, but honestly it travels literally more slowly in its orbit. All right. Then I've got layers of the sun's interior, 3 layers, and exterior, 3 layers. So here we go. On the interior, we have the core, radiative zone, and the convection zone. It's right here, okay? And then its exterior, we have the photosphere, the chromosphere, and the corona. Okay, so those 6 layers. Features of an active sun. So the sun goes through these phases, and right now actually it's kind of quiet. But when it's active, we can definitely have sunspots are the things that we track. There's a picture of sunspot. Other things that mean the sun is active, you can have solar flares, prominences, and a granddaddy of them all, coronal mass ejections. And as far as it cycling up and then down, they're looking at about 11 years. It kind of hits a peak, what we call solar max, and now it's actually almost near solar min. All right. Terrestrial versus Jovian planets. So the terrestrial planets are sometimes called the inner planets. The terrestrial planets are the rocky planets. So there's these guys. Then the Jovian planets are sometimes called the gaseous planets, and there are 4 these guys. Features of them, so know that, let's see, the terrestrial ones are rocky. They generally have limited moons, limited to no moons. Okay, actually Mercury has no moon, Venus has no moon, Earth has a gorgeous one, and Mars has 2 things that look like potatoes. So what do the Jovian or gaseous planets have in common? They have lots of moons. I didn't say this here. They have lots of moons. They do. And they have bands and rings. Let's see. Mercury's odd rotation. So I'm going to have some questions about each, well, not each, but a question here and there about some of the planets. So one of the things about Mercury that I want you to know is the fact that it has crazy, very hot daytime temperatures and very cool nighttime temperatures, and that's for 2 reasons. One is that it basically has no atmosphere to trap its heat, and the other is that it rotates so painfully slowly. Then I have Venus, thick and deadly clouds, and actually the gas in Venus atmosphere that makes it so hot is carbon dioxide, but its clouds are actually condensed sulfuric acid. So know that. Mars, a large volcano. So if I ask you which planet has this guy right here, this is called Olympus Mons. That is the planet Mars. So there'll be a question on there about that. Jupiter's long-lasting storm, I bet you might even know that before you took this class. That is the Great Red Spot. So know that that's associated with Jupiter. We've been seeing it for at least 300 years. Uranus' strange tilt. It looks like this. So whenever you see a picture of Uranus, I think these are both Uranus. Its axis of rotation basically lies in the plane of the ecliptic, so it kind of scoots around on its edge like that. So it makes it have some crazy seasons. What generally is Pluto like? And of course, Pluto is no longer a planet. Pluto is a dwarf planet. And Pluto is much more like similar, let's see if I have a comet. That's what I was looking for. Pluto is like a comet. And what is a comet? Comet is rock and ice. That's what Pluto's like. Gotta love it. Speaking of comets, there are two regions we find comets, and you're going to want to know those. One is and they're both shown here. That little dot in there, that's the sun. Of course, we have the planets orbiting the sun. We have this thing kind of in the plane of the ecliptic. That's actually called the Kuiper Belt. That's one region where comets are located. And even farther than that, kind of distributed spherically, is what we call the Oort cloud. So know those. Direction of a comet tail. So comets, remember, fizz as they get close to the sun. And so this is a neat kind of several pictures of a comet, April 26th through June 11th. And the comet tail will always go away from the sun. Even though it's going this direction, the tail goes this way because of solar wind. I just think that is so cool. All right. Meteoroid versus meteor versus meteorite. Okay, so a meteoroid is the space rock that is in outer space. A meteor is the streak, okay? And a meteorite is something that you pick up off the Earth's surface, a space rock that didn't all get burnt up falling through the Earth's atmosphere. So when we talk about meteor showers, we're talking about a bunch of potential streaks at this in a given evening. And this figure is kind of showing you what's happening. This is the Earth orbiting the sun. It's all about counterclockwise. And as it runs into kind of a chunk right here and a chunk right here, that I've circled actually is debris that's left by a comet. You can kind of see a comet orbiting the sun, and it leaves debris that the Earth passes through. And so we have an extra sort of neat sort of meteor shower. Go back. No, I guess I do need to go for it. Right. Oops, I think I need. All right, on to part 3. The Earth's moo and eclipses. Earth's moon and eclipses. So the term regolith is actually lunar soil, and it sure reminds me of like ash that you have left over from burning charcoal. There are two sort of features we see here on Earth with the naked eye. There are the dark regions called the mare, and there are the light regions called the highlands. Okay, yeah. The way this works is that let's see, far side of the moon. Oh, I don't see it. Do I have it on here? Far side of the moon. I don't see it. Well, I'll just have to explain it. So so this is the Earth, and of course the moon. I'll make this the moon orbits the Earth, right? And it's about counterclockwise too. And the moon actually spins on its axis of rotation as it orbits the Earth, as the Earth is spinning on its axis of rotation. And so the way it works is there actually is what we call a far side of the moon. And the far side of the moon is the side that we never see. So this is us. We're standing here looking at the moon, and we see the near side. So the opposite of far side is the near side. The reason we don't ever see the far side is because the moon is spinning on its axis the same amount of time it takes to go around the earth once. So it's kind of like a little kid who's like, you're not seeing behind my back, you're not seeing behind my back, and they're going around you, and they're also kind of spinning, rotating. Okay, so anyway, so I have, synchronous rotation. So this right here, the same spinning, same amount of time to spin as it does to orbit, same spin to orbit, that actually is called synchronous rotation. Okay, rotation. All right, now we get down to here. So the 7 phases of the moon, know those, all right? So of course this is full, right? When I don't see it at all, it's new. Actually, that's not on here. These guys right here are crescents. We have a crescent. I'll put a C for crescent. We have a crescent here. This actually is a waxing crescent. I'll put wax because I can tell that it's going to go from the right to, the right to the left, whatever it's doing. This guy is actually a waning crescent because it's going to keep getting more and more dark. So this is a waning crescent. Then we have our quarters. Okay, so this is first quarter, first Q, and this is the last quarter or third quarter. Either one would be great. And then that leaves these. This is our gibbous. I'll put a G for gibbous here, and this is our gibbous here. It just means that they're more than a quarter, but less than a full. So this guy is a waxing gibbous. I can tell because it's going from right to left. It'll keep getting more and more illuminated. And this guy right here is actually a waning gibbous because it's kind of got dark over there on the right. So this is a waning gibbous. So know those. Earth's tides and what causes them. So the way this works, and being here in Iowa, we aren't privy much to this, but it's the moon. You can see it in this figure. It's the moon actually that causes our oceans of water to be lifted up by where it is. And the Earth, remember, is spinning, rotating counterclockwise as all the while. And so we have a bulge of water, and this is your high tide. And this is actually gravity, a gravitational tug of the moon onto the waters. Okay, solar eclipses and lunar eclipses. They both happen because of kind of the way the sun, the moon, and the earth are. So this one right here would be a lunar eclipse. They call it a lunar eclipse because it's the moon that's getting blacked out. And what happens is that the earth is actually in the way between the moon getting lit up by the sun. All right. So if the earth wasn't in the way, actually this is what we would call the full lunar phase. So lunar eclipses happen when the moon is full. Okay, so solar eclipses, the sun is being blocked out. So here the sun is being blocked out by the moon. And it has to be just right. And actually if the moon, so the moon can block out the sun, this will always happen during a new phase. New lunar phase. Oops. All right. Parallax, what causes it? All right. Let's be on the next page.
I'm not sure.
It's not okay. So parallax. Oh, go back. All right, yeah, there it is. So it's kind of shown here where we have these are the observer. I'll put O for observer, and the observer is moving. So it's right here, and then it's right here. And notice that something relatively nearby, I'll put an N for nearby tree, looks different against the background. So this person sees the tree here, and this person sees the tree here. Okay, now if we take that tree and get it farther and farther away, closer to the mountains, actually as the observer moves back and forth, or a different observer is not going to see it move. That's called parallax. And we have a phenomenon where we can use parallax and we can see the stars actually kind of change location as the Earth changes location as it orbits the sun. So here's the Earth, and then 6 months later, here's the Earth. Now, if a star is relatively nearby, then it's actually going to jump here. If I'm here, this is where the star appears. And if I'm here, this is where the star appears against the background. So, but the star has to be relatively close. All right. So, celestial sphere. So it's a kind of a creepy looking thing. Of course, there's the Earth, and this would be like I think I showed you this in the classroom, but it had the stars kind of embedded on it. That's the celestial sphere. It's not that the stars are all equal distance from us like that, but it's a model that kind of shows how the stars are organized. So it's a hollow sphere with the Earth in the center. All right, on to part 5. So it looks like how light travels, the inherent delay. So light, you think like you turn on a flashlight and right away it gets to you, but actually it takes a certain discrete amount of time. It travels at a certain speed, the speed of light. And so if you were located 1 light year away, it would take 1 year for the light to reach you. Okay, so that's kind of how that works. So there actually is a delay when we get the light. So from the sun, it's about 8 minutes to get the light. From Mars, it's about 12.7 light minutes. To the nearest star, you're talking about 4.3 light years. To the other side of the Milky Way galaxy, you're talking about 52,000 light years. Okay, so there is definitely that delay. I just think that is so cool. Differences between stars. So we have differences in the color they shine, the differences in their intensity of their energy, we call luminosity, the difference in what's happening in their cores, as far as are they producing hydrogen, are they fusing hydrogen, are they fusing helium. We have a difference in how quickly or how slowly they live their lives and how they end their lives. So those are all major differences in stars. Star brightness scale, this is one of those, well, don't blame me, right? So the star brightness scale is kind of weird, and it seems backwards, because like our sun is about a -26 and Pluto is about a +15, so it seems backwards. Okay, so that sun's brightness scale is based upon basically kind of the dimmest. Well, I think that'll do it for you. Kind of know if I gave you a +15, you'd say it's very dim. If I gave you a -26, you'd say it's very bright. Stars are classified into 7 categories. They are down here, the O, B, A, F, G, K, M, where O is hottest and M is coolest. Hirschsprung-Russell diagram. Let's see. That's this what I call a scatter plot, and so usually they aren't drawn to scale, but here are these are all different stars. And the thing about the Hirschsprung-Russell diagram is you can see across the top the 7 spectral types, O, B, A, F, G, K, M, where we have the hottest over here and the coolest over here. And the thing about an HR diagram is we kind of have 3 types of objects. We have a section right here. Those are our main sequence. And then we have a section right here. Those I generally call supergiants or giants or red giants. And then we have down here white dwarfs. So those are kind of the 3 main sections. Then I have supernova. That is actually how a star that is more massive than 8 solar masses is going to blow up in what's called a supernova event. Now, and the thing it has in its core before it goes out is iron. White dwarf, let's see, slide. White dwarf actually is a relatively normal or low mass star as it ends its life. Here we go. This could be the sun. I know it just says a star, but this could actually be the sun. The sun is going to swell and become a giant, It's going to go into what we call variable stage. It's going to slough off some of its material. It's going to look beautiful in the sky, be a planetary nebula, and then it's actually going to come down and be a white dwarf, and that's a retired star. Planetary nebula. It's kind of an end part of a star kind of dying. One that's not going to blow up, right? Because if it's more than 8 times the mass of our sun, it will go supernova. But planetary nebula is kind of a gentle end to a gentle star. A neutron star is one of 2 types of objects you can get. So here we have a massive, this is a massive star, more massive than 8 solar masses. It's also going to swell and such, but it's going to blow up, and it's going to leave behind either a neutron star or a black hole. So the thing about it is both of these objects are very, very tightly packed material, very, very, very dense. And so there will be a question about a neutron star, which is one of the 2 options that are left over after a massive star goes supernova. Neutron stars actually spin very fast. Neutron stars, as they spin, they kind of shoot these kind of energy signatures out their axes. Excuse me. And so if we're in the path of kind of that whipping around energy, we'll see a blip, 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 and actually from it spinning, and that sort of blip, blip, blip is coming from a neutron star. So characteristics of a neutron star is very, very dense. Neutron star is mostly made of neutrons. And here I have protons and electrons have combined to form, oh my goodness, neutrons. I can see that didn't make it. Neutrons is the word there. So pulsars, the blip, 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 etc. That blipping is actually what we call a pulsar signal, and it's a signature of a neutron star. All right. Then wrapping things up, we go to the last part, and I've got just structure and dimensions of the Milky Way galaxy. So on my note card, I'd pretty much put this. I think this is really pretty good. Notice it says that we're about, from side to side, you're talking about 100,000 light years. It's got a thickness in general about 2,000 light years thick. It has a nuclear bulge in the center, and see, do I have, yeah. In the center of our galaxy is a black hole. Specifically, it's very large. We call it a supermassive black hole. Actually, most galaxies have them, as it turns out. It has 4 spiral arms. We are on one major spiral arm called Orion. So I would kind of jot all that down. The Milky Way in our nighttime sky, okay, sometimes people say, oh, did you see the Milky Way tonight? And this is what they're kind of talking about, this sort of kind of cloudiness. You have to have really dark skies, no moon, and it really kind of pops out. And so what you're looking at is kind of into the plane of the galaxy, our galaxy, when you're looking at this. I just think that is so cool. Dark matter. Dark because we can't see it, and matter because it has characteristics of matter. Most likely it actually has some sort of gravitational influence. So that's kind of what dark matter is. There is a common, so what you're looking at here is this is our galaxy, and our galaxy actually has dark matter, I guess I should say, do it this way, has dark matter in a large halo region outside our galaxy. Excuse me. Let's see. About done. How old is our universe? Dun, dun, dun. So I wanted you to know how old our solar system is, about 5 or 4.6 billion years old. And our universe is about 13.5 billion years. So I'm not going to ask you any questions over the Big Bang, which is kind of what we call the beginning of our universe. But how long ago did that happen? You're talking about 13.5 billion years ago.